So our next speaker is Alexandre Lacoste. While he is setting up his computer, let me introduce him. Alexandre is a staff research manager leading the UI assist team at ServiceNow. Since his PhD in theoretical machine learning, he has published influential works on foundation models for Earth observation, sequential decision making, causality, and various works in collaboration with Yosha Bengio. Prior to ServiceNow, he was the first research scientist to join Element AI and worked for 3 years at Google. He is also a founding member of Climate Change AI and an author of the seminal paper Tackling Climate Change with Machine Learning. It's our pleasure to host here Alexandra. Let's welcome him with a round of applause.
Thank you so much for the introduction. I'm very grateful to be here, surrounded by passionate people about a topic that's pretty close to my heart. Today it's gonna be more like a high-level talk, trying to see where we can go with foundation model and with already little bottlenecks on the road. But first, I'd like to ask myself this grounding question: what if we can build a model that reasons about the Earth the same way that GPT can think about the internet? But perhaps more precisely, why did Earth observation didn't get this GPT moment yet? Is it because it's a much harder problem? Is it there's not enough data out there to be able to serve us? Or we're just lacking incentive to get together and build this bigger kind of model? Or is it currently happening? We just don't know yet. But first, what do we mean by foundation model for monitoring? Which kind of capability are we expecting that it's going to have? Of course, I think we all expecting there's going to be some kind of good model multi-sensor fusion where you can leverage multispectral data, maybe hyperspectral data, some wind fields, elevation map or temporal sensing, infuse all of that together, just going beyond just the RGB optical signal that we're used to. Multi-temporal is also going to be an important part, being able to understand the different time step the satellite or UAVs are revisiting the same region often across time. And the temporal difference is not always the same. Sometimes it's a couple of days apart, and sometimes it can be a season apart. We're getting used these days to model we can talk with, where being able to express what we want, what we're searching for, like we saw in the previous demo, I think can be very exciting. But something that's underexplored here that I'd like to talk a little bit is very large context window for monitoring. We've seen this happening in the large language model. The context window has been increasing, unleashing very interesting application. But here we're still focusing on segmentation of small images in many cases. Of course, we'd like to have reasoning and the model being able to produce a report on what it observed. And also being able to communicate on the image that you provided, being able to communicate polygons to detect object, but it's not necessarily obvious because it has to reason back into the original image space. Temporal reasoning and forecasting. We can picture, forecasting the risk of forest fires in some region, and having calibrated forecasts, something very, very underexplored at the moment. And also pixel-wise output, being able to express itself through pixel by pixel to be able to produce masks, some kind of overlay you can put on your image. Some kind of any-to-any model, but perhaps with a little bit more focus on what matters for monitoring. But in between the downstream applications and the foundation model, there's going to be a list of a layer of tools. I'd just like to glance over that with you rapidly. we're getting used to chatting with our models, being able to put documents or image there. So obviously, like we would like to have some kind of chat interface where you can put your data set and perhaps search for a specific thing, a little bit like similar to the demo that we've seen, but a little more interactive. And even if we have those zero-shot models that we can interact with, we're still going to need fine-tuning. So the ecosystem of fine-tuning models, having a pool of open-source models we can fine-tune with, and having a bunch of fine-tuning tools in order to serve downstream application more efficiently is going to be necessary. But something that is just starting this year, the agentic stack of EO. An access that I'm a little excited about. Imagine being able to do deep research over all of your data and being able to have create a report on the fly about a topic of your interest. So it's your agent to be able to go back and forth and search information, and perhaps it can identify uncertainty in some area. And realize, okay, what if I could have more data here? And if there's an API for communicating with a satellite image provider, perhaps you can start asking, okay, are you going to have a satellite going over there? And then negotiate price maybe across different satellite provider, and then get more data, and then do the analysis again, produce an updated report. All of that can go, improve some existing application. Great, but there's no reason to do any of this if there's no downstream application. One of application that's going to see a lot of improvement with this usage of zero-shot models and increased capability is going to be disaster response. So you have newly acquired image of a disaster that just happened, and you want to find, what are the damaged buildings to be able to assess rapidly. Very important one. Agriculture and food security is definitely going to be served. There's a lot of untapped progress that can happen, both on the farmer side and on the regulation side. Farmer can improve precision agriculture, being able to forecast the health of your plants, forecast the yield. On the regulation side, perhaps we can uniformize a little bit and have better understanding of what's happening with farmers and equilibrate everything for everyone. A topic that's dear to my heart is the carbon biomass accounting in order to improve a carbon credit system. They can be a little bit more stable, more trustable. Of course, city planning and infrastructure monitoring. The elephant in the room, any progress we're going to do is also going to have benefits for military application. Great. So if we step back, on one side you have capabilities, and then in between you're going to have a layer of tools that we're going to build together. And most importantly, we have to ground ourselves in downstream application. So that's why we're going to jump into benchmarking. So if done correctly, benchmarking can help the community move together. We can guide new directions, we can open up new challenges, and we can also improve the quality of science. In many cases, paper is going to develop their new technique, and then they're going to choose some way of evaluating a couple data sets out there. They're going to show that it improves compared to a baseline. While this works for publishing, it's not necessarily comparable from one paper to the other. It makes it, can give an illusion of progress. But out there's more than 10,000 EO data sets. This is definitely enough for doing the benchmarking that we need, but how are we going to select the right subset in order to be able to know what we want? So we're going to start by enumerating a couple of desiderata that we would like to have from benchmarking. Ideally, we would be able to evaluate more than one capability. So if the goal is to evaluate a foundation model, to compare it to other, there's different capabilities that the model can have. We want each capability ideally on more than a few data sets. So we can have aggregated metrics, have some statistical significance. And these are challenging tasks where there's some progress remain to be done and we're not already plateaued. Leaderboard can help follow the progress. Okay, let's dive into that. So throughout the talk, I collected a few high picture like this. These are done through deep research. Of course, they tend to hallucinate a little bit. They make mistakes. But I did multiple deep research, cross-validated then, and a little bit hand-tuned all of that. So apologies if you've been working on some of these projects and it's badly categorized. But I think it's mostly correct for these kind of table. So these are different benchmarks for fine-tuning. So we're still in the fine-tuning regime, so you get a large model that's been pre-trained on some data, and you would like to evaluate how well does it do if I would fine-tune it on my downstream data set. All of these benchmarks correspond to a collection of data sets that are going to evaluate a few capabilities. Some of them are more specific. For example, FOMO bench is about forestry. And REO bench is more about robustness to noise. So the synthetically induced noise, realistic noise on images, some kind of glitch you can have from satellite noise, and then measure robustness to it. But then by looking at the table like that, we can see other axes, the verticals here. I find it very interesting. Where on the side do we see the mouse here? Yes, we do. So these two columns here have almost no representation. So this notion of evaluating for large context or for forecasting, not really out there in the field. So, perhaps we should start looking at it. So temporal, like most benchmarks, don't consider temporality here. So some of them do. Starting to do it, often it's just temporal difference. But I think there's a lot of new things we can do by working on temporality. Should definitely put that more out here. Another thing here, there's a column about open license. Just a note, I'm going to come back to it later if I have time. All of these benchmarks are open license, but some of them have commercial restrictions. And this means that if you're a company, for example, like Google, there could be legal action if you're just evaluating on that benchmark. So it makes it hard. Like we need to make effort to have free for non-commercial models. Okay, so now we're going to dive into GeoBench. This is one of the first project I did when I entered the field of Earth monitoring. And a little bit of a newcomer out here is going to be GeoBench 2. I was hoping to say it's out, but it's not out yet. It's just a few weeks of work. The GitHub is there, but the paper is going to be there in a few weeks. Okay, but let's talk about it. What is GeoBench 2? It's going to be 20 data sets. They're downsampled from the original data sets, your existing data set. So they're downsampled to be able to have a faster evaluation. They are all selected to be discriminative and challenging, meaning that we experimented with more than 20. I think it was 35 data set that we all converted and trained 15 different models. And the ones that were non-discriminative, meaning that it's kind of plateauing or it's hard to really tell if one model is better than the other, then we just discarded them. We also broke the benchmark in 10 different subsets. Here it makes a table. We see the different data sets that we transformed. And all of these check mark here is representing, is it part of each of the subsets. So these subsets here, they represent capabilities that we're trying to evaluate. And so each of these capabilities, they contain multiple data sets. So the positive side of that is if you care about temporality, you don't have to evaluate on all the 20 data sets. You can only focus on 4. And you're still going to have a leaderboard that you're going to compare to other model that perhaps evaluate on all the data set. All fully open source license. It was not necessarily easy. We had to drop very interesting data set because they had the -NC associated label. And we evaluated on more than 15 different models. Okay, so that was it for the fine-tuning approach, but there's the zero-shot model that are becoming more and more interesting for the field. It's a very different way of evaluating these models. We don't necessarily, we don't have to fine-tune. So the evaluation part is much easier in that sense. And there's already a couple benchmarks that are out there. But as we see for the verticals here, there's still a variety of capabilities that are underexplored. Luckily, multi-sensor is there up to a certain extent, but temporality is very ignored still, and large context and forecasting is not there either. And also, seems like our community is not a big fan of leaderboards. These can be convenient and help the community move forward. So this year, with MBZ UAI and IBM, we worked on GeoBench VLM. It's different than GeoBench. This it's meant to evaluate the VLM, the zero-shot model. So we're going to dive into that one really quick. So it's meant for zero-shot evaluation. There's 8 categories of tasks in that benchmark. For example, temporal understanding. An example is count the total number of damage building visible in that scene. So the model is going to have to look at both images and be able to understand which buildings is damaged. And it's multiple choices to leave no ambiguity for the evaluation. There's also object counting and localization and non-optical imagery. So, and the whole benchmark, there's over 10,000 instances. They are all human verified, and they're non-ambiguous evaluation. And also there's a provided leaderboard. There's still limitations. There's only 2 steps for temporality. And there's no large context window over the evaluations. There's no forecasting. Perhaps it's going to come later in our next version. Now I'm going to move on to bottlenecks. So across the working on different projects, there was a few obvious, but when you start working on it, but at the high level, it's not always obvious. And I'm going to just describe a few of them. So if you start collecting image for self-supervision, come out there uniformly across the planet, there's a large amount of data that's just not interesting. Per se, there's no pattern. I mean, there's some amount of pattern, but it's mostly noise. It can be desert, ice sheets, or forest. Also here, we see well enough. This is Landsat, the size of one single pixel. So you miss all of these details here, Sentinel-2. Even though it's very low resolution at 10 meter, it's still a very large rectangle. And so these are all open access, but if you want to go to better resolution, then you have to go to get commercial data. So it's hard to get something that's going to gather all the patterns that you care about on the Earth. But for a project we did in collaboration with Satellogic, we collected the data of 15 terapixels that contains multi-temporal data. This was the aim was to build a large data set that have a strong self-supervision signal. So Satellogic was kind enough to give Creative Commons image without the non-commercial limitation. And this is the part where it's 1 meter resolution, and there's also near infrared, so it's at least 1 band beyond RGB. Also, we collected the Sentinel-2 and Sentinel-1 image. They're all collected across the world and together, so that you can inform your Sentinel-2 from Sentinel-1 and vice versa. There's also multi-temporal. There's up to 10 time steps for each location. So there are kind of cubes collected together there with overlapping, so you can create some self-supervision signal. We also collected hyperspectral data. Very interesting because it's not often that you can get your hand on such data. It's still open source data, but very limited coverage, unfortunately. Now, bottleneck 2 that I've been hinting about is non-commercial. This, if we can, make a little effort to get rid of those, that would help. They help both on the training side and on the benchmarking side. So if we collect large amount of data, then commercial company, if there's a -NC, cannot really use it, or maybe they will use it anyway, and they will develop a big model, but they will have to hide which data they use for training it. A little bit like speculation about Llama. It's been trained on a lot of copyrighted data, but they don't mention what they train on because it's going to be legal action against them. So it makes less transparency on the training process and so on. So benchmarking, so if you make a beautiful benchmark out there and there's some data set that has -NC, then if you're a commercial company, you cannot evaluate on it because you can have legal action. So it's just slowing down everyone. So if we can just focus on the one with no -NC. So recommendation, if you build a new data set, you can try to make an effort. You're partnering with people, partnering with the provider. So you can make an effort to negotiate to remove this -NC. Sometimes it's not going to be possible. Sometimes there can be some compromise you can make by maybe lowering the resolution of the data. They're going to be more inclined to release it. You can try to get a grant or partnering with a high-profile association to create a beautiful story behind it. Also important, communicate the license and the process clearly. There's, if there's a data set, there's going to be three components to the license. There's going to be the code component. Often there's code associated. And then there's the labels that you create has their own license. And then the image itself may have a different license. It's important to communicate the tree license, communicate where it comes from and how you got it. Because we've been in a situation where legal department is looking into that. It's like, yeah, it says it's CC BY. But I'm not sure it's not clearly identified, and sometimes people, they just stamp without knowing what they're doing. So leave a little bit of traces, put more than just, this is the license. This is going to help. Okay, bottleneck 4, the cost of satellite imagery. I was really interested where we're heading with that. If we're going to build a large model, then we're going to need to collect a lot of data, and especially the high resolution data. What's been limiting us in the high resolution and multi-sensor is the cost of gathering all of that. So I collected a little bit of data, put that plot here, and I was curious about some kind of projection. Like these are calculated number with just a few things, so take all of that with a grain of salt. But we see a trend where airborne or UAV imagery is going down much faster than satellite imagery. With satellite imagery have 6-year time frame for halving the cost, where airborne makes more sense. It's more 3 years, and the Moore's law is 1.5 years. So I just broke down the cost to try to understand what is the bottleneck. There's a lot of cost for satellite imagery that is, so by the way, this is a cost for satellite, not for drones. A lot of it, a big part of it is computer related, which is somewhat of a good news, meaning it's going to go down a little faster. The processing, the storage, the data transfer, transferring to the ground station, count for about 35%. The satellite part, the actual satellite that you have to build, especially if you want to have a high resolution satellite, you need either the lens with that, the optics. It's very heavy and expensive stuff. It doesn't follow Moore's law. It's more traditional engineering. So the cost to have, the time to have cost is more on the scale of 5 to 10 years. It's really one of the bottleneck. And one of the reasons I was interested into that is because we know the cost of launching stuff into space is going down very fast, but it turns out it's not a big part of the cost. And Of course, it's other people, other costs like people and the market. But perhaps there's going to be a little bit plot twist to this cost forecast. Maybe the agentic stack, if we're able to have agent negotiating prices and lowering the friction to get those satellite images, maybe it's going to amortize costs a little faster, and we're going to be seeing a different dynamic. Or maybe I'm just too optimistic. Now, I'm going to dive down into some potential research axes where I believe we should put some effort into improving our field. We saw in the previous talk a mask autoencoder. It's a very famous one. It's an elegant solution to sensor fusion or even temporal fusion. What you do, you patchify everything and you put some encoding associated to each patch. This encoding is going to encode the temporal, the spectral information, maybe the sensor information, and also the spatial information. So, well, in our case, it's starting to be a lot of information to pack in this encoding and associated to the patch. But the advantage of that is that once this patch is identified like that, you can ensemble it into a set of sparse elements of your image. So this means that you need all the sensor. Sometimes you have SAR, sometimes you have optical, sometimes you have elevation, or sometimes you just have part of the image on one side and the part of the other side. This is what allows you to train in a mask autoencoder fashion, where you just mask some of the input and then try to predict the output. It's this notion of a sparse set that allows us to do that. So many papers have been working with this principle, and it works to some extent, but there's a core limitation to this approach is you're losing important fine-grained detail. And for example, here, if your job is to identify cattle in the field, this is a project I was working on. We're trying to count cows in the Amazon rainforest to track illegal deforestation. But if you patchify your image 16 by 16 or even 8 by 8, you're losing this core information. I mean, you may be able to recover a little bit of it, but it's like your small element, the detail is going to be clumped together. So we see there's a clear trade-off. So VIT and the mask autoencoder are good for sensor fusion, but can get fine-grained details. On the other hand, you can play with Bottlenecks and SWIN architecture. These are very good at fine-grained details. We observed very good performance on some data sets, and both GeoBench 1 and GeoBench 2. These are the two architecture that stands out compared to most VIT architecture. The problem is that you're back to this dense d-dimensional tensor. You cannot break it down to a sparse something. And so, yeah, we're back to square zero in terms of sensor fusion and the scalability of training this whole thing. So what can we do? Would there be some kind of hybrid approach where we can combine both? Not sure. Do we need to develop new architecture in order to be able to move forward? You tell me. It's open research. Research axis number 2, I've been talking about very long spatial and temporal window. I was curious to see if there was a trend, so this is yet another deep research. I tried to get the receptive fields of many of the so-called foundation model that are out there. Receptive fields is kind of, there's some things are patchified, so it's the number of token, the size of the token can vary, so I try to get a metric that's common to all of them, so it's a kilopixels. So with the y-axis that we see here is the number of kilopixels of the receptive field. So one thing that's interesting is there's absolutely no trend. It's more like everyone is working under some 3,000 kilopixels of receptive field. And what I mean by a pixel, RGB is 3 pixels here, so if there's multiple bands or there's multiple temporality, these all add up. So it depends on I'm calculating, multiplying this kind of cube. There's 3 outliers, but there's 2 of them that are, at least when glancing at the paper, it seems more like a rapid decrease of exponential aggregation at different layer. So it's kind of really stated as like big window because you're not integrating information across all of this thing. So SkySense was one that seemed to be a little bit more involved into that. But what are the research axes then? Maybe first question, should we even go larger? Does it even make sense? I mean, am I just like wishful thinking or translating from the LLM world where we clearly see a trend increasing? Which kind, if we do, which kind of data set would require such thing? I'm thinking that yield forecasting or some kind of agriculture where you get weekly screenshot across the year and you have the whole crop. I can integrate a lot of information if you ask specific difficult question where the information isn't there. So perhaps integrating all of that information would allow you to respond interestingly. So, but we need to build this data set. If they are out there, please let me know. And yeah, of course, the obvious research in that direction is like explore different architecture and training method. You're gonna have to scale it up. This is the kind of research that require a lot of GPUs. Now, as a third research axis, there's a lot of work that needs to be done on VLM as well. We've seen rapid progress this year. This is another table that shows different VLM for EO reasoning. What we see is it's still largely around language and object detection or object image captioning. There's very little multi-sensor, very little multi-temporal. On the benchmarking side, we saw that it's ready, but on the training, there's little work on that. Perhaps because there's still a lot of progress to be done just on these things, or perhaps just because the data, like George was communicating with us, like it's hard to get this text and multispectral match together. Same thing with temporality. But yeah, we should try to collect these new benchmark, this new data set. Great. Now let's talk about research axis number 4. The agentic stack. So there's already, this is a very new field. When I started this presentation, I thought it was a little bit forcing to start talking about agent, but there's actually quite a bit of agent out there already, and there's already 2 benchmarks. My other agenda is about agents, more like LLM agents, able to interact in user, like computer use agent or web agent. So I'm excited to see that happening on the E world. So if we go back, if we focus on the benchmark side, there's two benchmarks here, one done by MBZU AI. This 436 human-curated queries, and they are close to the VLM kind of queries, I would say, but they are interesting because they're complex, where it's probably a good idea for your VLM to break it down into different steps. For example, you have to calculate something. You first have to detect some element in the image, and then you have to do some calculation around it. So like you have a sandbox where you run code and then come back to it and then detect something else on the image. Technically, a VLM could do it in one shot without doing tool calling, but an agent perspective can help you improve the score. On the other hand, you have Univ Earth, Google Earth Engine as a tool, and it's about researching information and then bringing it back. Now, on the agent side, there's already a variety of agents. We're going to see soon why. They are coming out all over the place. One particular one is Google Geospatial Reasoning project. I only saw a demo. It's not usable yet, but you see that chat window where you can start querying on the Google map and have like Gemini interacting with your data and search into database. Very impressive demo. I encourage you to go see it. But what are the challenges ahead of us for that? So what's interesting is that agents and tools, they can be coded in a few days. or even in the afternoon if you vibe code it. MCP protocol allows you to create very easy tools around maybe QGIS, or maybe you wrap up some Earth model that you have, Earth observation model. You just wrap it up as a tool, and then you can have GPT or Claude, and they're going to start calling them as tools, and you can start interacting. Very cool things. So making agents is not so hard, but making good benchmark takes months. And then this subfield is gonna branch out also into so many different subfields. It's gonna be like, hey, if we can make an agent for this, we can also make an agent for that. And so there's many startup ideas, or many, like this notion of being able to query images from satellite provider through an API sounds very appealing to me. But we're going to clearly need a benchmark, because I don't want to release an agent out there that's going to buy $1 million of remote sensing imagery for no reason. You want to be able to calibrate it and be able to make sure it's doing the right thing. It's also a little bit hard to frame as a research direction. Like making a benchmark, you bring it as a research paper, it's accepted, and it's a lot of work, but it's accepted. And then making an agent that does something, and trying to make it small bench, it's harder to have an accepted paper. Anyway, so this is still a research axis. It's hard to do research on agent. Great, so I went a little faster than I was expecting, so I can answer some questions. There's time over. I'm gonna go back to slides that I hide because I thought I was having too many slides.
Well, thank you very much. Are there questions?
Thank you for the interesting talk. I have a questions about agents, namely what you mentioned at the end, that agents and tools can be called very quickly. Perhaps that's true if we think of agents like some pre-trained model that we just feed some stuff in context. But don't you think that if we want to progress there, we want to actually look into data sets and training them with reinforcement learning to actually be able to solve truly complex tasks?
I completely agree with you on that. And yes, you can create environments, a synthetic environment where, perhaps a fake environment where you can do this, and then you can start doing reinforcement learning to improve this. Having worked on that for a couple of years on the UI agent side, it works. It's very slow progress, and then you get this new agent that you show that Llama, your open source model, can make that progress, and then you get this new closed source model that comes out, and out of the box it gets really good performance. But yeah, so the two worlds exist. So I definitely don't want to discourage that, and it's definitely a really good axis of research. So yeah, creating synthetic environment where you can do reinforcement learning for your agent sounds a very appealing project for me.
Yeah, thank you.
Thank you for the very interesting presentation. My question is more related to the data fusion side of it. Our brain collects data from our surroundings using multiple senses, but we rely more on some than on others when there's conflicting information. With more and more satellites and eyes in the sky, do you think do you see some similar trends on what type of data and satellite images we can rely more on?
You mean, well, because I don't know how to answer that one, but there's availability on one side, and then there's being able to rely on it. There's some downstream application that would really benefit from having different kind of data. Perhaps something that can penetrate the ground. Optical data is not able to penetrate the ground, but some bands or some radar is able to go analyze soil. But if we want to make progress in there, we're going to need to start collecting data sets for that.
Yeah, the physics of capturing different data, satellite images is different, and we somehow know some of it. But how much we can rely on different tasks to deal with this data and to make decisions based on multiple data sources. That's what I was alluding to.
How much can you say, are you meaning that since there's a lot of, the spatial data is not so available, it's not going to be as reliable? Or?
It's more than whether you think that some types of data based on the physical properties of how they are captured and what they mean will be more relied upon when making decisions, because we see more and more multi-sensor data areas of interest. Yeah.
Yes, so I do think if we make progress on sensor fusion, then perhaps we're going to be able to perceive more directly the information that we care about instead of inferring it from patterns. So that could definitely help on reliability.
Thank you.
Are there more questions? I have one, by the way, in the meantime. You talked about this advantage and disadvantage of transformers and then CNN architectures, especially compared to SWIN against the other VITs, right? And then the pros and cons about that one is good for the fusion, the transformers, and the other is more about the fine-grained details. I didn't quite understand what makes to do so, although you commented about this block tensors not having these sparse things, but it's still not clear on what particular application we're talking about. What are the difficulties? Maybe you can give some more details on that.
Yes. So you want to know why exactly? So there's on one side you have the SWIN and the ConvNext that are working directly with this dense tensor thing, and it's able to have a more conventional approach. And we see in metrics when we measure on benchmark compared to VIT, the performance is a little higher. And the hypothesis is that it's able to make better usage of this fine-grained information that we see in the image. Because we're often limited by the resolution. We wish we'd have more pixels, but we don't have it. Like 0.3 meter is the best we can get. And we need to make the best we can out of these pixels. And so ConvNext seems to be one of the, it's more conventional, convolutional architecture. On the other side, if you do VIT style, you're going to have to patchify it. Some people reduce the size of patches. I think it can work. So you're going to have maybe 4x4 patches. So then you increase your granularity like that. I haven't made explicit experiments to understand that. But if you keep it to 8x8 or 16x16, you're kind of, if you're in your patch, you have 2-3 cow in it. You won't be able to distinguish. It's going to be like a linear prediction or some kind of blob embedding of different components. So you lose very important information if you're going to patchify your image. So, but when you patchify it like that and you bring the encoding, spectral, temporal, and all of that with your patch, then you don't have this dense image anymore, this dense tensor, and you can have a sparse set of components. And this is how transformer works. It works with a set of components. And this sparsity allows us to turn off some sensors. So sometimes you only have RGB, sometimes you only have SAR. So we have different input, or you can have 2 inputs at the same time, or 3 inputs. You can have multiple time steps. So it lets you being more flexible on what you put in there.
So when the fusion we're talking about is really diverse kinds of sensors.
Yeah.
When you okay, and also about this the prediction task, because I was thinking about if you are doing this dense prediction task of, let's say, fine-grained semantic segmentations, then transformers also do quite well, right? And there it doesn't seem to have a problem of patchifications, because they also have to still make a predictions at the pixel level, right? And then is it like then is it intrinsically different in these settings we're talking about in the geospatial settings, or it's still unclear why it works with the similar logic that you describe on image segmentation, fine-grained image segmentation, transpose on data.
So you're saying that transformer do express some fine-grained details. So it can work up to some level of fine-grain. So I don't have a clear answer there. You know, like it's kind of the limit of my what I distilled from experience. But so I think it's able to have some understand some subspace that's going to be able to be precise at the segmentation level, but it's going to be limited. I think
my question is more about, is it like generic problem, or are we talking about more specific the geospatial data that has different problem in this regard?
I think it's more common in geospatial data that you're limited to your resolution, right? When you have come an image from the web, it's often high resolution, and you have like high-level semantics, object that you care about. But I think if you, even from normal image, if you start caring about many very specific details, then this patch level is going to hurt you a little bit more. And this is something we see a lot in maybe 1/3 of geospatial application, where if you could have better pixel, less blurry, or a high resolution, then it's going to be better. And this is where this patch thing is hurting a little bit.
All right, thank you very much. Is there any more questions? If there are no more questions, then let's thank the speaker again for the amazing talk. Now we have a coffee break right outside. You can grab the coffee. But in the meantime, I also want to update you regarding the posters. There will be posters hanging there, not necessarily being presented now. If there are the authors around, you may paste them, discuss about, hang out during the coffee breaks. Those posters will be better presented tomorrow. Tomorrow is more spotlight talks related to those posters, as well as the poster presentations will be more active during the breaks. Today also feel free to go over and reach out the authors and discuss about the posters. All right, see you in half an hour.